And again, this goes back to doing your due diligence of like, what is your use case? If you just need it to drop a Docker binary on the machine, run it, and have something running, it's great. But if you actually need high I/O throughput or various types of stability, you should actually get in and tune these things. And there's documentation on how to tune the device mapper backend. But what actually happens by default, and it's fine if you don't care about this, but what happens by default for the device mapper backend is that it needs 2 block devices. For thin provisioning, it needs a metadata block device, and it needs a data, where all the actual storage happens, block device. The metadata can be much smaller, and you obviously want as much data as you're planning on using. So what happens if you want to start this and you haven't actually reformatted, like repartitioned your storage device or set up additional LVM volumes to give it a block device? That would take finagling up front, and everybody wanted it just like push button simple. Just, I want to be able to drop a Docker binary on it, start the daemon, and Docker run. So to make this happen, what happens behind the scenes, if you're using device mapper and have never touched it, the very first time that it goes to run, in varlib docker, it creates 2 files. It creates a metadata file, and it creates a data file, and it truncates them so that they could grow up to 100 gigs for the data file and up to 1 gig for the metadata file. And it then attaches these both on loopback devices. So then it now has 2 block devices that are mounted to 2 files on the file system. So anything that you're doing inside of your container, any image that you download, anything like that, actually fully has to traverse a loopback device and then onto a file on the file system. So if you're doing any applications and you're defaulting to device mapper and you're looking for high I/O, you're going to cry. You're gonna look at top and you're gonna see that it's just your application is thrashing, and the next thing in line will be the kernel loop device, like the loop logic is just hammering because it's just sitting there iterating, traversing the tree of paths. So various distributions, or even like in the Project Atomic, the default installation for certain OSs that now are using this in production will straight out of the box repartition and give it 2 block devices, even if they're just LVM logical volumes. It will give them, a thin provisioned metadata device and a data device, and it speeds it up by orders of magnitude. And now you actually have something that you can work with and not just files floating around. So, device mapper. Btrfs. Who's played with Btrfs at all? Yeah. What are your feelings about Btrfs? Yeah, nice, okay, good. So, I end up using Btrfs frequently just because it is also very fast. I feel that it's in many ways more stable than AUFS, but it still has interesting corruptions. I mean, I have such high hopes for it. And yes, the bug has the bug has been fixed where one day you boot up your machine and your entire disk is just not there. That bug was fixed, that's great. But especially in the Docker scenario where you'll download images, and many images sometimes, or you have it on a build box that's just sitting here iterating, and you have many untagged layers and lots of dangling images. Sometimes this can be in the order of thousands of subvolumes and subvolumes on top of subvolumes. Or somebody will try something like Docker in Docker, and then it's like, oh, it's a Btrfs device, and it starts doing more subvolumes on top of subvolumes and thousands of them. So even just recently, CoreOS has been on Btrfs. So if you've played with CoreOS, who's played with CoreOS? Good. So plenty of people. So even recently, CoreOS has switched from Btrfs, I think, to OverlayFS. So some of their recent ones, they're bumping up their kernel to the 3.18 kernel, and now trying out OverlayFS. OverlayFS. Who knows or is excited at all about OverlayFS? Yeah, like 3 hands. That's great. OverlayFS is pretty great. It's a union file system that's been heavily iterated on, and I think, given past experience, especially in the kernel community, that it's become such a deliberated process to make sure that it's very ready. And even if, like AUFS, there's sometimes patches carried and communities that evolve around a technology, kernels and Git trees that are floating around that just support it. OverlayFS has been heavily iterated through and has finally merged into the 3.18 kernel. Everybody's excited about it, and it is seeing lots of good fixes. It is brand new. So I'm sure there's going to be things that people find as it goes along. There was a few different kernel calls that had to be tweaked or modified and now have like a 2 appended to them because they just can't quite work the old way, so just extend the API. But even companies like Red Hat are actively working on getting like SE Linux involved in this and getting this firmed up so that even this is an option for other use cases, not just Docker. So good prospects and good hopes with OverlayFS. As far as Docker is concerned, it is very fast. It is already in Docker for at least a version or so. You have to have a 3.18 kernel. So for most people in a production case, that's going to be a stopper straight away. Just because if you're using whatever distribution's kernel, which I recommend most people just don't mess with your kernel, like just use what people give you. Because if you mess with your own kernel or you go off and use some kernel that you found somewhere and then you report buggy issues, you're not going to get a lot of help. So please just, move along the best path possible, but it is in the 3.18 kernel. So if you have access to that or you have systems that have access to that, feel free to play with it and give feedback. Does that make sense? Yes, question?
Is this the best solution that you recommend today? Or maybe not very solution?
There is no clear winner. I knew that was going to be the very next thing people are going to ask. There is, and this has been a sore spot, I'll say, because there's lots of attention given to all of these different drivers. OverlayFS, people are having high hopes for, but even like in Docker scenario, they can only have so much hope for it, as we're testing it. So right now it looks like the best one, but as the kernel continues to iterate, we just have to work at that pace, and we can be involved in that process, and you can be involved in that process, but there are certain things that just have to move at the pace of discovery and just aren't there right now. A lot of folks hoped that was ButterFS, but as folks are running big production systems and pushing things to the far nth, they're finding that maybe even ButterFS is not quite there. Hopefully one day it will be, but not yet. AUFS, while it is fast and performs, there's plenty of edge cases that it just is quirky and you get into really awful kernel digging around, and nobody's wanting to do that because it's really only supported by canonical. So nobody really has motivation to go fix it when it's canonical's problem, and if they are interested, that's great. But Device Mapper, there's a lot of motivation behind it, but it's got its own drawbacks, and it takes knowledge. It takes you have to get involved in Device Mapper to make it good. So most people that just want Docker run, they throw Device Mapper out as quick as they can because they're not even getting involved in the process. So pretty much learn for your use case. And at this point, there's various companies that I've worked with that are now finding that maybe ButterFS is okay for a build machine, maybe because it just iterates and it can go through it so fast that they'll have a CI machine that's running Docker that is on ButterFS. And once they have a good build and it's promoted, that's fine. And if they lost that, if it somehow became corrupted and they had to remove it, big deal. They've already promoted the ones that they liked and done something with it. But then in production, they might have certain certain things that make sense to run on AFS, or might have like longer systems that they'd give a direct block device to Device Mapper for high I/O, and that's fine. So it might just be that you have to get so involved that you know that certain machines are running various like permutations of configuration. So learn your use case. They are not all equal at all. Any other questions about that? Okay. Yeah. So the layers are. And this sounds almost silly because of how so many people have thought about now layers are immutable, but they are largely mounted read-only. So as you go to run some container all the layers that have gotten it there, they are mounted and they are read-only so that you're just on top of them. They're still on the disk, and they're down there, but the immutability of them is that they're mounted read-only, and everything that happens on top of that is on the snapshot. I'll kind of allude to that. I'm alluding to that now, but I'll touch back on that in a minute. So one of the other big performance issues, and I didn't make you a matrix here, just because some of this is still in flux and may change as we go along and find better ways to do things. But one of the other big performance differences when you come to some of the different storage backends for Docker is that the way that they do diffing, because diffing is fairly essential to the storage graph drivers. And that's because anything that you do, whether you say, how big was this runtime? I mean, how big is the image? I'm going to go to commit this image. I'm going to actually pull in an image from the hub and lay it out on the disk. All of this frequently has to do with how is it applying it on to, like it literally graphs it onto the disk, and it uses different diffing logic to do that. One of the reasons that AUFS is fast is that it can actually do certain diff operations natively. It can just look at operations and say this is how it differs from the layer underneath it, and it's fairly quick at that. Some of that it keeps in memory, that's why it eats up memory. Other graph drivers like presently Device Mapper do this natively. It actually has to walk and say, is this here? Is it not here? Has it changed? Has it not changed? So it ends up coming up with like a change list set of like, this is added, this was changed, this was deleted, you know, and it just walks through that. And so on various systems, it can be very fast. Many folks are now throwing SSDs at this because it can do it really fast and you don't even care. But in various scenarios, somebody will go to commit a layer and they're like, why did, you know, on certain systems that took milliseconds and other systems that took 10, 15 seconds. And it's this diff logic. So some of this, as we get more creative, might improve, but presently this is another big performance area. All right. Any questions up to this point? Yes?
It seems a bit similar to the concept of containers in Solaris from version 10.
Okay. I'm not terribly familiar with them, so in what way are you seeing that?
Well, I'm not very familiar with Docker, so.
Yeah? Good. So they had layered file systems, though, rather than just...
A container concept,
Mm-hmm.
I think a hypervisor concept, but there could be other. Maybe somebody in the room knows.
So it is interesting because that's one of the things, especially in Linux containers, that Docker has brought is the notion of layeredness to it, because there's LXC and it just points at a directory. So if you did layering technology outside of LXC, then it would use it, but it was not part of LXC. Systemd inspawn, it just runs in a directory, like rootfs. So that's one of the other notions, you know, in this whole Docker container world, that it kind of mixes those two worlds together. So perhaps I'll have to go read up on how Solaris did it, but I'm not terribly familiar with Solaris layering.
Thank you.
Yeah. So portable images. Whether you are building the image yourself or you're going to go out and try one from the Docker hub, this is one of the ways where you say Docker pull or Docker run something, and if you've like got it on a local registry or the hub, it just discovers it. It says, hey, I do or don't have something called BusyBox. Where can I resolve it? All of this magic, per se, happens with tar archives. Tar archives are great and amazing, and they're a very fundamental part of Linux, but they are, anyhow. So tar archives are used for all of this magic. There's a few places where the image tar archives will just live. Yes?
Yeah, question, how do you handle ACLs with tar, because it really sucks.
So the question was, how do you handle ACLs with tar? Which aspect of ACLs are you thinking about?
When you have, I could imagine a use case where you want to have ACLs on your images, so not anybody's allowed to read or do any action with it?
Okay, so to the actual tar itself.
Yeah.
Okay. There are, it's not built into the platform per se. There are now enterprises working around having that kind of ACL access to the image and its archives. This is, I mean, like Docker's got some ways of doing it on their side of seeing that you've got public and private repositories on the hub. That's technology that's internal to Docker and the hub. There are, I'm sure, other registries that are working on ACL access to it. Okay. I thought you were going to go into a more file system level, and there was features added over the last year about extended attributes like file ACLs and having the header support for them, and that's been a pain in plenty of people's butts for the last year because certain file systems like the AUFS file system actually do not support extended attributes, X-adders. So if you do something on like a CentOS or Fedora box and actually set like extended attributes of any kind, and then move that over to AUFS, you won't be able to read them. So, and they have no incentive to add that feature, but it just isn't there. Anyhow, so there's that also. So tar archives. When you actually push an image to the Docker Hub, or a registry, even if you're running like your own registry, the daemon actually tars up and it walks through each one of the layers, and it pulls off and it actually sees this layer is, again, different from the layer above it because of these files, and it produces a tar archive of just those files. So it's a very involved process. It's not just like there's files sitting around. It actually has to go through and do a diff operation of each layer every time. So when you go to push an image, it walks through each one of the layers, and if anybody's built a Docker file that's like 100 different steps, it's going to take a little while because it's going to sit and walk through each one of those. So that's why you end up seeing people have Docker run and then like continue new line, so that it's all on one Docker run invocation, because that's one layer. If you put each one of those on their own layer, it might be more easy to read, but less performant in different cases. So you choose your battles. It goes to create a tar archive of the diff set of each one of those and some metadata, and then it pushes it to that registry or the hub. When it's sitting out on the hub, that tar archive is fairly static. Like it's not meant to change ever again. People will pull from it. But if you pull from the hub, it grafts it onto the disk. If you turn around and push it to a local registry, it might be the same image name, but the tar archive on that new local registry is not actually the same tar archive as the one out on the hub. You could MD5 it or whatever SHA-1 Summit, and they are different archives because it has been through a mutation process. M times, A times, C times. Thankfully, even though AUFS can't support X-adders, so in a runtime of a container, you couldn't deal with X-adders, the graph operation that pushes and pulls them can do it at the file system level. So that was one good one, that you can actually pull certain things and it won't strip off extended information off of the files, but you can't interact with it inside the container. But yeah, they're just fundamentally different tar archives. Or even this one, when you start reading like a tar archive, which just steps through the file records in it, this one might have started at bin / and this one started at /etc/. I mean, like they're not ordered or anything. It pulls it and pushes it. But even further, tar archives are used internally for Docker for all kinds of things. Copying from one directory to the other. If you go to Docker build, you see it say uploading context. It makes a tar archive of its context and pipes it over to this daemon. Anytime that it does simple copying operations or committing operations, it passes it up and over through a tar archive to do that. So tar is heavily involved here, and it's actually thankfully allowed us to make a couple of good upstream fixes and improvements and optimizations for the Golang implementation of tar archive, which is exciting for various reasons. So the tar archives are there. So despite the images being mounted read-only in the image runtime, the files are actually all on the disk. So if you ever got curious, you could actually start walking through varlib Docker. So like in Btrfs, if you have an image with, the hexadecimal ID of dead beef, then you could actually CD into varlib Docker, Btrfs, subvolumes, dead beef, and the full SHA-256 length sum, and look at the files there on disk. It does make it problematic that because the files are kind of in transit and the tars are thrown away and there's not certain validations set in place, that you can't actually see if your sysadmin has gone and munged a file on the disk. Some of these kind of features are just not there yet. We're working on them, but they're just not there yet. So it's meant that if you're going to run like a build server, you're going to run access to this, you need to make sure that you know that that machine is safe. Multi-tenancy, having access to boxes. Everybody has hopefully heard all the security concerns of if you have access to run Docker run, you basically have root on the box, even if you're a limited user. So these kind of things, if the layer's been modified on disk, it might still have the same image ID. It could be a very different image. So there's effort going on to protect that. But it has meant that in the way that Docker has evolved, that stuff like signing images, since the tars are not completely immutable and holy and the tar is preserved, that signing is kind of a problematic thing. If you yourself have an image that you've built, honestly, I would however you're going to handle the ACLs and access to the image, that's one thing. And most people are concerned about that because of secrets, and that's a whole different conversation completely. But if you have an image that you've built and you are going to share in your local network, you might want to put it on a local registry so it's easy. But if you want somebody like open source projects, maybe the hub is easy for you to do that. But if you wanted to have people have absolute assurance that what they've pulled is the image that you as a project have built, your best bet is actually to do whatever permutation on the machine. You Docker save that thing to a tar archive, which it itself is a tar of tar layers. You can sign that thing. You can checksum that thing. You could put that foo.tar up on your hosted server, and it might be large. But at least they can pull that thing down and check the detached signature of that thing. And then even if their daemon throws it away, they can at least have some level of assurance that what they've pulled is the thing that they've got from the other party. They can check identity. They can trust that identity, at least for that one moment. This kind of internalized process is being worked on Docker heavily right now, but the timelines are still up in the air because of some of the underlying issues. So if one of these types of concerns is a concern of yours, there are external ways that you could do it. It would not necessarily be as easy as Docker run, but you can figure it out. That's pretty much what I've got, and 5 minutes left to go. Questions? Yes?
What setup do you recommend for the wind? I think you said already which there is no wind, but if you're running some kind of applications like Redmine or something with containers, what kind of file system or distribution you use? Or even you go directly to CoreOS,
So the question was largely, I guess, recommendations for which ones to use. Sometimes, and I can't even say, for like a project like Redmine, if your bottleneck is I/O or whatever, if your bottleneck is just being able to load up, there's other things that are being worked on. That one of the hopes that even about OverlayFS is that it can do caching, like page sharing between similar PIDs, because a couple of the technologies, they're actually different inodes. Once it layers up, they're different inodes that get running. So even if you're running Apache in two different containers, the kernel sees that the user bin Apache that it's using, or not user bin Apache, but whatever, that they're different inodes, so they map to different memory segments. Well, in OverlayFS, that they can actually map to the same inode, so there can actually be, memory sharing within the kernel. And so there will frequently be times that it just comes down to you having to figure out, like, running what is the scenarios of this type of environment, which one runs best, which one is most supportable, which one has the least amount of magic and just works. And for various application stacks, I have no idea. Honestly, it's just investigation. And so some of those kind of industry best practices for this application versus that application, I feel like are still in the works. People are still doing this type of experimentation. There's actually on the Red Hat blog, there's even the Docker folks refer to the Red Hat blog where Jeremy Eder, Germs, you'll see him on IRC as Germs, from the enterprise performance team, has done some pretty impressive benchmarking of different cases and different types of like trials and which graph driver performed in different ways. And it's pretty clear that there's no clear winner. I mean, like, they all do different things differently. So you have to do a little bit of experimentation. Other questions? Yes. Has anybody done which? Yes, there's active pull requests going on and conversations about that and testing and trials with it. I think some people are hesitant about it and some people are overly excited about it. I have not formulated an opinion on it yet. One of the things, and this is really a call to action. It's a big project. It is moving fast, and it's popular and exciting. But like every open source project, it still has components like ZFS that need deliberation, that needs involvement. It needs even sometimes maintainers, because this is all Golang. So these are not just dynamically loaded plugins to say, in my environment it happens to run some other permutation of storage driver. All of these things are actually compiled in. They're all part of the same thing. They're in the Docker core tree. So they need maintainers. And even in the short time that Docker has been around, some of these, the maintainers that wrote the code for these drivers have already left the project. So in certain situations, we're actively looking for people to say, do you want to become a subject matter expert of this thing? Great, come on. And so when more people are saying, hey, do you want to do Ceph or Gluster and ZFS and whatever else, they're all exciting, but the concern is often that we'll add something that then that person moves on and nobody knows how to support it. And you have new people trying to become a subject matter expert of it. So ZFS is a very active conversation, and I invite you to get involved. Just go to the Docker GitHub project and search for ZFS, and you'll find the conversations. Okay, we're time's up. Thank you all. Feel free to come and find me. VBATs.